Carboxylic acids and esters. They have something in common. So what is that, you can ask me? And this is the carbonyl group. So in order to introduce those two new functional groups, we're going to start drawing the carbonyl group. So that looks like that, right? So it is but of course it doesn't just float in air by itself. So it has to be bound to something else by virtue of the fact that carbon is tetravalent steel, right? So for the carboxylic acid, so what we need to have is the attachment of the OH group to the carbonyl group. And this is going to be our carboxylic acid functional group, right? So again, the functional group by itself doesn't just float in air, so it is attached to something else. So here we have this something else, right? And this could be just simply a methyl, for example, or a million of other possible alkyl chains, right? So maybe it is going to be also an aromatic ring, right? So it's also a possibility. But for now, we'll just do something like that. And then we have here an example of a like specific carboxylic acid. Specifically, this one will be called ethanoic acid, right? From ethane, as you might see from the name, from the sound of the name, and also the fact that it contains two carbons, right? So consequently, we use the root ethane from ethane, right? So the parent alkane from which this theoretically was derived. So then we need to take a look at esters. So they have a notable difference, but also some significant similarities. So they again need to contain the carbonyl group, right? So in this situation, we are going to attach the not OH to the carbonyl, but OR. And by R, we typically have some sort of, what's that, alkyl chain, right? So here, for example, again, we can just have some sort of alkyl chain. Let's just use the good old methyl. And now here we have our ester group. Again, so the ester group is typically attached to something else. So maybe it's going to be methyl, ethyl, phenyl, many other possible alkyl chains here. So, but that's going to be kind of the difference that you can see between the carboxylic acid functional group and the ester functional group. So, moving on to nomenclature, right? So we need to be able to name those compounds, and what we need to do is show the example of some sort of carboxylic acid, such as maybe like this one, for example, right? So we have quite a bit of stuff here, quite a bit of carbons, as we can see. So now we're going to introduce the acid group, right? Again, by the virtue of its structure, it cannot just be put in the middle, right? So like with the hydrogen from the OH connecting to two other carbons, for example, right? So because the hydrogen cannot do that, right? So it can only have one valence. So, and that's it, right? It can only form one bond that it used to form to the oxygen, right, in the carboxylic acid. So this is going to be our only option, right, to like show the carboxylic acid on a terminal carbon in the chain, right? So then we might have the substitution going on, right? So like this. So for example, maybe let's make it ethyl this time around, right? So now we're going to count, right? So we're going to count starting with the carbonyl carbon of the carboxylic acid. So we're gonna, of course, found the longest chain, right? So here we have opportunities, 1, 2, 3, 4, 5, 5 long-ish. Let's check other options, 1, 2, 3, 4, 5, 6, 7, 8. Wow, 8 carbons, right? So let's use that as our longest chain. So we're going to number all the carbons just to show that we have 8 carbons indeed, right? So then we're going to circle our substituent as such. So that's the one, right? So it is a CH2CH3 technically, so which is ethyl overall. So, and what we're going to do is say, well, on the third carbon, there is ethyl, right? So it's going to be one substituent only. So if there are several of them, we are going to arrange them alphabetically. So that is going to be our kind of like one of the rules that we need to consider, right? So, but here we have only ethyl, right? So like 3 ethyl. On the third carbon, so that is 3. On carbon 3, there is ethyl. So then what else? 3 ethyl, right? So then we have acid, right? So we need to have the word acid in the name of the like respective carboxylic acid. And we need to use the root corresponding to the number of the carbons in the longest chain, right? So, which is going to be derived from the parent alkane with 8 carbons, right? So that was octane, just a straight chain of 8 carbons. It is octane. So we are going to use the root here. So 3-ethyl. Then we'll continue to the root, right? So and then we're just going to use the part octane, right? So then for the acid, carboxylic acid, we are going to use the suffix oic, OIC. So this is our root, right? This is our suffix. 3-ethyl octanoic, what is it? It is an acid, right? So like we are basing our name due to the fact that we have the carboxylic acid functional group here, right? And then we name this compound based on the presence of the carboxylic acid functional group. So that's it. So 3-ethyl octanoic acid. So that's a little bit ugly 3, but it is, let's just erase it. So it's going to be 3 here, like believe me, right? So 3-ethyl octanoic acid. So just like that. So named it. So now let's move on to like other things, right? So such as the nomenclature of, guess what, esters, right? So again, it's going to be good to show using the example. So, and then here is our example, right? So let's maybe make something like that, 1, 2. So here, maybe this, right? 1, 2, 3, 4, 5, 6, 7. Okay, let's make it 7, right? So here we go. So it looks like an acid, but instead of H here, we need to have some sort of like alkyl typically, or maybe aromatic substituent, right? So, so far our scope of substituents is like quite small because we are at the fundamentals of organic chemistry, right? So we don't go into some kind of like crazy substituents yet. So, but here we might have, for example, I don't know, let's make it phenyl, right? So this guy, C6H5, if you kind of like identify all the atoms in the structure right here, right? So this is just drawn in the line angle fashion. And it still means that there are carbons and H's, right? So, but they're only implied, right? So that's kind of like one of the major features of the line angle structure. Implications and like relative fastness of drawings. So this is just like a CH piece here, apparently. So here we go. So what do we need to do, right? So first of all, we need to look at what is attached directly to this oxygen in the ester group with 2 single bonds, right? And we need to circle this group, right? And then we'll call it, what's it called? It's called phenyl. It's not phenol, it's phenyl, right? Just one subtle letter difference, right? So phenyl, then we're going to take a look at the acid that kind of like was used to synthesize this ester, presumably, right? So the acid is here, right? So that's the one. So if you just imagine this big blob, right, without phenyl, but with an H here, you will get the respective carboxylic acid, right? So now let's name the carboxylic acid, right? So the carboxylic acid would be here 1, 2, 3, 4, 5, 6, 7, right? 7 carbons in a chain. So that would be, what's it? Hexane, heptane, right? 7 carbons in a chain corresponds to the alkene heptane, right? So, but the acid will be obviously heptanoic acid, right? So, if it is an ester, right? So, if this heptanoic acid is part of an ester, which has the phenyl instead of H in the heptanoic acid, we need to acknowledge that we have phenyl, first of all, right? So we'll just write down the name phenyl of the substituent, right? That substituted H on the what was previously used to be the heptanoic acid, right? So imagine there is an H, right now there is not an H, but phenyl, right? So this guy, C6H5 in this small circle. So now heptanoic acid will retain the root, right? Heptan, but we will not use oic acid anymore, right? So we're going to use the suffix oit. So which signifies that we convert it, right? So that we have a look at the kind of like substituted essentially heptanoic acid, right? That turned into the ester, right? So basically to the educated person, that would be kind of like known that, okay, phenyl heptanoate. So this combination of words means that, okay, well, And then this characteristic suffix says that we're going to have an ester, right? Which was derived from heptanoic acid, right? That's what we need to keep in mind, quite literally. So once you decipher this name. So heptanoic acid basically lost H on the OH group specifically and switched that H to phenyl, right? So that's essentially what we see in this picture. That's why it's important to draw in organic chemistry. So phenyl heptanoate. So if you have, let's say, instead of, for example, like phenyl, let's make some like challenges. I mean, not challenges, but additions, right? So maybe like this one. Okay, great. So I just did it. So maybe let's take a look at this one, right? And then here we have our famous isopropyl, right? So then the name will change, right? So, but the kind of like principle will remain, like the backbone of the name will kind of like stay, right? The sequence in the name. So we're going to have instead of phenyl, now identify this as an isopropyl, right? So isopropyl, 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 and it's not heptanate anymore because in this blob we have 1, 2, 3, 4, 5. So we have 5 carbons, right, in a chain. So it's going to be what? 5 butane pentane, right? Pentanoic acid was used to make this ester, right? So then consequently, instead of heptanoate, we are going to have pentanoate. Pentanoate. Isopropyl pentanoate. So that's the name, right? So that's what the nomenclature of esters esters looks like.